let's go back after the battery change break. Okay, this equation that you see over here is the same as what we have previously, correct? So this Ls over Lu come from Ls over Tu, right? Ls over Tu is you add velocity term. Oh, this is different one. Ls over Lu is the one without x. It's this equation. So that's the equation 3.11122. So, Sweta, what is the page number for 3.122? What's the page number? Pardon me?
100.
100. Okay. Alright. So that equation, I copy it here and rearrange it. So WL is rho L vs LAP, right? That's WL. Move these two to another side, so it cancel with this, cancel with that. We get this equation. Okay. We know that x, we know the expression of x, substitute the expression of x in. So we have VLTB equal to VTB minus all these things. So rearrange this equation. Move it to the left, move it to the right. We get this one. Good? Not good. So I just cancel these two to this side. Move HLTB to the denominator. And then rearrange a little bit to solve for that term. Okay? So now then, next step, I put this term back into this equation and I get this term. Okay? Multiply it, rearrange it, do the integration. Oh, next to Sveta. Modia, how do I do the integration? How do I get this term? The last term, where is that from?
Integrating that part. VTB minus each of us.
Okay, integrate that part. We actually don't have to integrate it, right? Because we just multiply it. VTB is not a function of length in the field, right? VLLS doesn't have anything to do with the field. HLLS doesn't have anything to do with the field. So integration of something that doesn't have anything to do with the field is LF, which is that, divided by LU multiplied by the original part. Just that. So the part left that we have to do the integration is this. So I try to do all this to tell you how do you get the equation in your book and to show you that the equation in your book is correct. Okay? Then that's VS. We rearrange it. I copy it from the previous slide. Okay. Multiply this thing in. Get these two terms. And get this equation. What do? Rearrange, cancel, add some part together. You see, this term, Vega, this term and the first term combine into this term. Why is that? No reason. So you agree with what they said? He didn't even say yes. Do you agree with what they said?
Yes.
Yes. So Ls plus Lf equal to Lu over Lu is 1. So we get this equation. Okay? Alright. So we can also, instead of recheck W, we can recheck VSL. So this equation can be used to recheck VSL. Good? So next step, I rearrange it, and at the end I get the equation in your book. Okay, so this is to show you that, okay, these are the same. This part just rearrange, move it around, okay, and it gets to the point where it is the same as your book. So your book is fine. Right? Then I copy it again. Okay, next part, I try to show you that when we do overall mass balance, you see that overall mass balance, that equation, at the end, what we get is V mixture equal to VLOS multiplied by HLOS plus VTLS multiplied by alpha LS. That I try to show you. Okay? So mixture velocity is a holdup times actual velocity plus holdup times actual velocity. But for gas, use gas velocity and use gas holdup, which is alpha. Okay, that's equal to Vm. And the step that I used to show you that is this. After we get the equation from your book, okay, we do the same thing for the gas phase. Similarly, for gas phase, VLS just change to VTLS. HLOS just change to alpha LS. Okay, VTB stays same. And HLTB change to alpha. H change H to alpha, just that. These things stay the same. So similarly, we get this equation. And we know that VSL plus VST equal to Vm. And so we add VSL and VST together. See this VSL, this VST. So we add two equations together, just that. So this term becomes this part, right? This term becomes this part. Good, right? That's first equation. Put everything from the second equation to this part. Okay? Add them together. Then the blue part. I take this blue part and I show you that. Okay? When we add HLOS and alpha LS together, it's equal to 1. Right? So it's equal to this. The red part, I show you that we have H and alpha, add them together, is equal to 1. So I get this part. Substitute it back. This show me that Vm is a weighted average of the velocity and the holdup, just that. And this is consistent with the case of horizontal flow. When we say Vs is Vm, okay? Is it consistent? So if it is horizontal flow, double Hubbard, who should I ask? Siri, is this consistent for the case of double Hubbard? How do you know that? So for double Hubbard, we would use what? Instead of VLS, we use Vm, right? Or Vs, they are the same. Vm multiplied by HLOS plus VTLS is Vm, right? Because they are the same. Vm multiplied by alpha LS. So take Vm out, we get Vm multiplied by H plus alpha. H plus alpha is 1, so Vm equal to Vm. So this equation is also valid for double Hubbard case. Now you're good? Okay. Alright, so the point to show you actually is this. We will calculate slug unit holdup. do some derivation, and at the end, I want to show you, so that is 3.128. At the end, I want to show you that slug unit holdup does not depend on the slug structure. Okay? We don't need to know film height at every location. We don't need to know that. Okay? If we just know liquid holdup in the slug body, and if we know VTB, okay, translational velocity, and if we know VSG, VGLS, or instead of VGLS we know, instead of VSG, VGLS we know VSL and VLS, we're done. We can calculate holdup of the unit slug. Okay, holdup of the unit slug, not holdup of the film part. But if you know the holdup of the unit slug, you can also calculate holdup of the film part, right? Let's say Doppler-Hubbard model. We assume VGLS to be the same as VLS to be the same as VM. So gas, liquid, and mixture move at the same speed inside the slug body. So if I assume that I know holdup of the slug, can I get the unit slug holdup? Une? I think so. Use 3.128, right? So because we will know this term, that term, everything. Okay? Then we get unit slug holdup of 1 unit. So if we assume that film height is uniform, like in your homework, how do we get holdup in the film zone? Raymond? Can we get film height without solving that ODE? No? No? So if we assume film height is uniform, can we get film height? How do we get it? Okay, let's go back a little bit. We use this equation. If you assume that the film height is uniform, okay, this equation, first of all, is valid. Whether your film height is uniform or not is valid, okay? The meaning of this is volume multiplied by length equal to volume multiplied by length of each part. Okay, holdup multiplied by length, average holdup of the slug unit multiplied by the length, give you some kind of volume. Okay, holdup multiplied by length equal to holdup in the slug body multiplied by length plus holdup in the film zone multiplied by the length of the film. So, does it make sense? You may think about it like holdup multiplied by length multiplied by AP. That gives you volume of the whole pipe multiplied by the holdup, give you liquid volume, right? That's on the left hand side. So for the film part, we use volume of the film. Volume of the film is volume, not volume of the film, volume of the pipe in that have a length of LF. So that volume is AP multiplied by LF. Right? Volume of the pipe that has a length of LS is AP multiplied by what's that? LS. So then cancel AP for the whole equation, you get this equation. Not clear now. I have to type it for you, right? Okay. Need to type it for you. Okay. How about this? A sub P multiplied by L sub F plus A sub P multiplied by LS. equal to what? AP LU. Okay. If you think about the liquid part, this is a whole pipe volume, right? If you think about liquid part, you multiply this by H what? LTB, right? And you multiply this by H of LS. And this will be H U SL. Oh, what did they do? U LSU. Okay, H LSU. H LSU. HL of slug unit. Okay. Liquid of slug unit. Cancel AP. No more AP. So cancel that. You get this equation. This equation is for the case where everything is constant. If your holdup is not constant, you integrate it, right? So you get that equation. Okay, just have to integrate for the film zone because for the slug body zone is constant. Alright. So from this equation, you see we have two ways to calculate HLSU or slug unit holdup. One way is what I have told you, that one, right? Another way is HLSU equal to 1 minus alpha. Okay, 1 minus alpha. Alpha is a y fraction. So to calculate y fraction, we use the same approach. This one. So instead of h, we use alpha. Instead of h, we use alpha or 1 minus h. So HLSU also equal to this, right? Same approach that we do it earlier, but this time has 1 minus. So second term is alpha, 1 minus alpha is h. And this is equation 3.126. Okay? In your book. Where's 3.126? Arya? Oh, you don't have book? Okay, sit more there. You don't have book. 105? 100. Okay, we still on page 100. Alright. Previously, we have VLS, which is this equation, okay? VLS, I copy it here. Okay. So VLS equal to something that we derived early on. Then I rearrange it to get the value of that integration. Integration from 0 to LF of HLTBL. Okay. That's I rearrange it. And then you see this whole part, I put it over here. That part. Right? And I get that as the HLSU. Okay. Then the right hand side, so blue term come from this blue term. Okay. That blue come from this 1, 2, 3. Become that. The rest, this term is from that term, that is that. It's just arithmetic. Okay? Is it correct? I think it's correct. Then rearrange it a little bit. I get 3.127 equation in your book. Okay, equation in your book. And from previously that we derived earlier, Vm equal to VLS, HLS plus VGLS, alpha LS. Put it in. Then we get 3.128. So this 3.128 tell you that we can directly calculate holdup without solving the feed profile. Isn't that cool? You like it, right? Do you? Yes, you like it a lot. It is matter when, is this equation only for horizontal flow? Can it be used for vertical flow? What do you think? Who read the book? Except Sveta, of course. Okay. Except Sveta. Read the book, please. What we are talking about is just 3 page. Okay, if you answer okay, page 100, page 100, page 101, that's the right answer already. So you may not even open it. Okay, 100, it's in page 100. So this time, when we look at this, HLRS is about 0.7. Okay, VTB you can do VTB equal to 1.2 multiplied by VM plus 0.54 square root GD or something cosine theta, and VGLS, V alpha LS. So everything that you have here is enough to approximate HLSU. Okay. Similarly, if you happen to have HLSU, you can use this equation to estimate your HLS too. Okay? Let's say you have flow in the pipe, you capture everything and assume that that is HLSU. Then you can use this equation to calculate HLS somehow. But one measurement wouldn't be enough because when you trap it, you cannot trap right with 1 slug unit, 2 slug unit. Sometimes you get 3.5 slug unit, 3 and 9.1 slug unit. So it's not really slug unit when you do the measurement. But you have the relationship between overall holdup and holdup in the slug body. This is what that is, okay? VGLS, how do we get that? Okay. VGLS, how do we get that? If we don't do the measurement, we can use this equation to get VGLS on slide 43. That's let's have some physics behind it, but yes, it's empirical. Okay, now you know that there's a relationship and you can jump ahead to do the homework. So can you do the homework? This is not Dr. Hubbard yet, or this is not Taitel and Barnea yet. This is part of it, okay, but not that point yet. Homework is nothing to do with Taitel and Barnea. You can just use this. So in homework, one of the questions you are asked to not calculate the film height, but you are asked to directly estimate the average film height. You may not be able to get local film height. If you want to get local film height, you need to do RK45, right? But you can get average film height. Okay? To get average film height, you use 3.128. Is it page 100? Yeah, use this. When you use it, you assume VGLS is the same as VM. That's that, for horizontal flow. And it is correct for horizontal flow. You know slug body holdup. Right? You know slug body holdup, this term. You know this one is the same as VM. You know 1 minus slug body holdup. Then you can calculate HLSU. From HLSU, you can use this equation to calculate average film height. Right? Average film height. Can you? Yes, you can. Film height. Alright. That's not real Taitel and Barnea yet. Let's talk about real Taitel and Barnea. Yes.
So that means in the whole 1.6, you don't expect us to use RK45, though, you're saying?
No, you don't use RK45 or you don't even use Euler or anything. There's not any of that. You can just do it. The last question is the same question as in the exam. But this time I give you the hint that the mixture velocity, average velocity times 2 is not the same as Vmax. That's the hint. Okay. So now you are going to do it right in the homework. Why not? Yeah.
And close book.
Close book? Yeah, it's close book. Yes. Okay, let's do it this way.
What is shit?
Use your first cheat sheet that you make, and then add another 2 cheat sheets into it. How about that? Is that better? So you can reuse your previous cheat sheet. You don't have to write everything one more time. Is that better?
Really?
You can oppose that, and I will say, okay, we just do everything in the constant bus.
First, can we do a previous, first part of example, like true, false?
I haven't made it yet, I don't know. I haven't made it yet. True, false? Yeah, I like true, false. Oh, it will always come with the negative point. It will always come with the negative
What
point.
is the philosophy behind the next?
So that you don't guess if you don't know. So if monkey do it, get 50, you do it, you get 50, what's the point, right? So I want to know that you're different than monkey. Good? No random guess. You may have educated guess. Okay, you may think, okay, you are 90% correct. You made a decision.
Yeah, but how do you then know if it was an educated guess or a random guess?
I don't know. I look at the score.
So you assume it was?
I look at the score. The score will tell whether that's educated enough, guess, or something. That's a penalty for you. Yes, question.
Yeah, I think you have to make an
For equation 3.128.
Yes?
Yeah, for the assignment, I mean, it's not perfectly horizontal, so is it still applicable?
It is. Even though it is 90 degree upward, horizontal, 45, 60, 70, 80, this is correct.
What about upward? It's not horizontal.
What about downward? Downward flow?
Upward.
Upward flow, upward vertical?
Title upward.
Or Taitel Hubbard? Doesn't work. But this is also applicable for double Hubbard.
So we can't use that ordinary differential equation, right?
You can, but it's wrong.
No. Yeah, because it's upward now.
Yeah, you can, but it's wrong. Okay? You're too fast, right? We don't have to talk about exams, it's easy. I will make it easier. I'll try to make it easier every time. Okay. Like second exam is easier than the first exam to some degree. So liquid film can be turbulent and 3D, right? It can be 3D. What do you think? Do you think it's flat? Can it be like shaped like this or something? So it has a free surface. But Taitel and Barnea is only 1D model. It is 1D model. Taylor bubble coordinate is used in Taitel and Barnea model. Z is the opposite direction of the flow. So Z move downward like that. Okay. Do you know how to increase the size of this laser pointer? Or you cannot. Okay. So this is common equation from Taitel and Barnea. I don't show you any proof. Okay. We just copy and paste, have it. It's the same as in your book. And we say that, okay, this is Taitel and Barnea. If you want proof, please prove it for yourself and show me. Okay, if you want proof, I don't show you any proof for this equation. It's just pop up. But I tell you term by term what that is. Okay, this term, v dvf by dz, that sounds like acceleration term or something, right? Or convection term in your Navier-Stokes equation. This is a potential dp dz. There's a friction, gravitational term, and another gravitational term. What's that about? You see the last one, additional gravitational term. Rho g cosine theta.
Change the height.
So because that's change of the film height. Do I have the proof whether this should be negative or positive? No. I just copied it and put it in here. You just need to see how does the result look like. Don't believe it yet. Let's see the result on how does it look like. Okay. So if you read the original paper, last 2 years I have students read the original paper and try to revise it. But this year, okay, let's skip it. So we have force due to the difference in the liquid height, hydrostatic head, in the positive z direction. So this height is higher than that height. So we have additional g cosine theta term. Okay, good. G cosine theta is in this direction. So that is to account for the difference in the liquid height. Additional hydrostatic head. Okay. We have equation for film and equation for gas. Alright. Now it's kind of tricky. So Arya, what is VF here? What's the page number?
Yeah.
100 or 101?
101.
101, okay, of course. So what is VF here, Arya? Is that film velocity?
Yes.
Actual film velocity?
No, it's
Kind of relative velocity? What about G over here, VG? Kind of relative velocity, right? So you can see over here somewhere in your book below equation 3.130 that VF is VTB minus VRTB. VG is VTB minus VGTB. So this VG is not the actual gas velocity. Okay? But when we calculate shear stress we have to use the actual gas velocity. Okay? If you haven't read the book yet, read it, okay? It's $75, right? Or you pay more than 75?
Yeah, but shipping.
Oh yeah, it's a little bit more. Okay. Tau I and tau G are in the positive Z direction, or opposite to the flow direction. Okay. Gas phase tends to slide over the liquid surface and lower its center of mass. Does it make sense? So when we have gas go over liquid phase, so liquid height shrink, and center of mass move a little bit down. Okay, I ask you here, what is dPdZ? Akin, what is dPdZ? Yeah, change of pressure with Z, right?
Yeah.
So what is the direction of Z? Backward, right?
Opposite the footer.
Opposite to the flow direction, okay? So you need to know that the Z is opposite. Let me derive this. AF, film area, AG, gas area, SF, film parameter that wet with the wall, touch with the wall, okay? So you have everything. Can we solve this equation? Somehow we can do it. And this is somehow. What is the formula for SF? If you know the height, can you calculate SF? Which page number? What about 3.67? Yeah, page 67. Separated, yeah. Okay. Can we solve that equation? You have seen this equation from Taitel and Barnea, right? It looked like that. I didn't give you any proof. Can we solve it? So eventually, you do some math, and then you get this longer form. So this form is similar to double Hubbard. Not identical, similar. Okay? The concept is the same. Everything on the right hand side is a function of HF, film height. And we use the same approach as double Hubbard. Okay? Same approach in Jeshen. How do I calculate critical height? Set what equals 0. Critical height. Don't tell her, she's talking with your way. The bottom part equal to 0, right? Denominator of this part, this long equation. Your question, how do I get equilibrium height? Pardon me? Upper part equal to 0, okay. Alright. So the starting point is the same. We solve it. And you get, oh, I didn't show you. When you solve it, you get something similar to what you get earlier for double Hubbard, several dots. Solve it by RK45. Okay? Good?
So the again difference is of
G cosine theta. Another one doesn't have G cosine theta.
Okay, so not really. Because it says he's getting rid of slug without activating slash.
We are going to talk about pressure drop separately. It's a little bit more. So this equation, okay, let's go back that we skipped earlier. So parameter in each equation, you do understand it, right? Okay. Tau F definition is the same. Tau G definition is the same. Use VGTB. Tau I is the same as stratified flow. VGTB minus VRTB, absolute sign multiplied by that. Friction factor use Brasse's type equation. dF for the film part 4AF over SF. dG, the denominator is SG plus SI. Fi, you may use 0.0146 or something, or 0.014. Okay, because we assume okay, if it's stratified AV in the film zone. So other parameters are the same. What do we do? Alright, equation 129 minus 130, the top one minus the second one, we get this equation. So the term that is related to dPdZ is gone. Good? The term that is related to dPdZ is gone. And we use X for gas and X for liquid. The relationship for X of gas and X for liquid to get these two equations, 3.137, okay? Not okay, okay? It's similar to the X equation that you have, okay? Which part in the film that VLTB is higher? Lower Z or higher Z? That VLTB is higher. Lower Cheng? Lower Z. So when it closer to the tail of the slug body, okay, VLTB is high, is highest, right? Okay. So we have equation for VF based on X relationship, right? Okay. So we use that equation, then we do take the derivative dV by dZ, we get this, and dVg by dZ, we get another one. Substitute these two into your combined momentum, 3.136. 3.136 is after you subtract it from each other, right? We have dV by dZ and dVg by dZ. Substitute those in, okay? Have this equation, some kind of long. Rearrange it more. It becomes like that. Equation 3.139. Good?
They don't have X and Y.
We have Z. You want X and Y? So this is the height with length based on that model. And if you, okay, I have one more in left. If you think about it, what happens when theta equal to 0? Okay, and you may want to think, what happens when theta is more than 0? If your theta is more than 0, you still have this term in the middle, right? Which do something. Previously, in the double Hubbard model, if your theta is more than 0, which equation? Could you tell me the page number for double Hubbard model? 90 something? Oh, 96. For double Hubbard model, on the top part, we have two terms, tau f and sine theta. Tau f, so this term, they are similar to, this term is similar to double Hubbard, right? And sine theta, the last term is not quite the same because we have this. We have gas. Okay, this term is not quite the same. But when this model can predict backward flow of the field. Okay, see you on Monday. That's it.
question